All right, so yeah, next topic, causality. Thanks actually for also coming back. It's great to see you all still here. So Pearl, the godfather of causal inference, I've got a bit of a man crush on this guy. All the impressive achievements of deep learning amount to just curve fitting. So cheers, that's basically everything we do here. So just a bit of curve fitting, no worries. Representation learning should move towards representations of causal world models. So essentially what we're saying here is that what we're doing at the moment is actually just exploiting correlation. We're exploiting associations between data points and distributions. And if we want to move up in sort of the rungs, or Pearl's rungs of sort of understanding and intelligence, we're at the lowest rung right now doing deep learning, then we should take more of a causal approach and be able to sort of derive an understanding of what actually generates our data, what's behind the structure in our data. Sholkopf said this as well, so he's sort of big in the machine learning world, and he's also advocating for it. I think there was a little bit of a sort of interest in causality a few years ago, and then it died out a little bit, but now it's coming back. It seems to be popping up in all the workshops and all of the summer schools, so I think it's well worth being aware of. It's going to give you a very sort of brief sort of overview of it. It's a world in and of itself. So as I said, becoming increasingly popular, but it's relevant for loads of different things, including debiasing, disentanglement, fair encodings. The only reason why I put these in here is because these are the ones that we're actually doing today. So there's a whole load of stuff that causal inference is useful for that we haven't even scratched the surface of. Other fields are, but they're doing it with much simpler data sets, in a statistical way. So, for instance, medical fields are using it a lot to infer sort of what actually causes a change and isolating that cause rather than just there's a correlation. And obviously that's a major problem in statistics, is sort of disentangling correlation from causal effects. So it's important also for understanding black box inference. So all the things we do is also sort of tends to be black box. We don't really know what it's doing. So explainability in ML, explainability in AI is also a really big important topic now. So we try and understand what our network's actually doing when it makes a decision. And it also gives us insight for latent variable modeling and generative structure. So, I want to sort of tickle your fancy with it a bit, because I think there's a lot to be done when it comes to sort of building deep learning up from the bottom rung in terms of understanding and exploiting associations into actually understanding what's going on in the world. Because I went to one on action recognition recently, and it was all just like, well, can I recognize an action? There's no understanding of what actually has to happen in that video. It's literally just, is there a basketball in it? Probably playing basketball then. It's like, no, they're bouncing it. It has to be bouncing it. It can't just be a basketball in Tesco's. Like, they have to be bouncing it, So this is sort of incentive to really sort of push the boundaries a bit. So I'm going to give you probably what I feel is the most important concept in causality when you're sort of being introduced to it, and that's called independence of mechanisms. So this little sign here means independence, if you haven't seen it before, and we're going to use two examples. This is just one. This is for altitude and temperature. We have a causal sort of worldview, which is that altitude is related to temperature somehow. We know a bit more than that as well. We know that actually the arrow only goes in one direction. Right? If I heat a city up, it doesn't start coming off the ground. Right? If I heat myself up, I don't start floating. Okay, maybe there's a little bit of that with gas and so on, but otherwise it's this way around. So as I go up in altitude, I see the temperature fall, and that's the relationship that we're sort of modeling in this scenario. This independence of mechanisms thing states that the conditional distribution of temperature given an altitude is independent of the distribution of altitudes. Now, when I say that to you, it probably means like next to nothing, but I want to sort of maybe explain it with a different example, which is even more intuitive. Imagine I have a barometer that measures pressure, and there's a storm outside. What I will frequently see is that whenever there's a storm, my barometer falls. But if I go in and I try and fiddle my barometer to push it into a different position, it doesn't cause a storm. There's an asymmetry there in the relationships that is captured by this arrow, also captured by these independent signs, but isn't captured by all of the calculus we tend to use for probability. So all of the stuff you've done with probability, we stick an equation in the middle. We can flip stuff around however we want. There's no sort of causal interpretation there. There's no directional interpretation. We lose all of it. It's totally symmetrical. With the maths that we get taught generally for say like the master course or what we tend to use, the arrow could go either way. Right? It doesn't matter. We're just using one to sort of find an association with the other. But in reality, that's not what goes on. in reality there is a direction there, and we should build that into our models of the world. So with the barometer, as I said, if I move the barometer, it doesn't cause a storm. But there's a little bit more to it than that, which is that the probability of my barometer reading a certain value given a storm is completely independent of whether or not, how likely it is that there's a storm. It could be that the weather changes, especially with climate change. Maybe we don't get storms anymore, or maybe we get way, way more storms. Regardless, it doesn't change my conditional distribution, which is the likelihood of the barometer being a certain value given a storm. So I hope this makes sense, because there's this asymmetry that exists, which means that it doesn't matter what happens to the marginal distribution. In this case, it's altitude, or it could be the probability of a storm happening. There's no information about this contained in my conditional distribution, which might sound bonkers. Like in some scenarios, you just think, well, surely if I know the distribution of weather stations, I already know the temperatures because I know there's a link there. And you might be able to do that, but what you're actually doing is inference. You're working backwards. Essentially, the distribution of weather stations is completely independent of the distribution of temperatures given altitude. Okay, so recognizing this independence of mechanisms is crucial in being able to build these associations and relationships into your models. And this has impacts for semi-supervised learning as well, which is actually an anti-causal scenario. So if it was the other way around and temperature caused altitude, then these wouldn't be independent, which would mean that if I changed the distribution of weather stations, I'd actually change the relationship that describes the relationship between temperature and altitude, which is obviously bonkers. So when we're dealing with most of our probabilistic sort of models and so on, we don't really build this in. Judea Pearl came up with do calculus, which is a way of incorporating this causality notion and this really fundamental asymmetries that exist in the world into the algebra that we use. I haven't seen it here in this department, but do calculus is a way to sort of start incorporating that. And until we do, we're kind of just stuck with associations. So is there a correlation between the two? Yeah. Don't know why. Just is. So how do we relate this to VAEs? With VAEs, we've got a latent variable model, and there's an arrow, which again we can't capture using traditional probability, which is we can flip around, do whatever we want with it. So what we can do is actually start, I'm not going to go over do calculus, but I'm going to start introducing that independence here, and to see how that relates to what we already know given the previous sections of this talk. So we're saying that these generative factors are responsible for generating our image. And that's actually our world model. When we're modeling these things, this inference process of variational inference has imbued within it the world model that we assume to be the case, which is that in here is going to contain the things that caused my images, which is actually a majorly big assumption. Like when I actually look at them, are they actually the things that caused my images? Luckily with faces, it seems to be actually quite convincing that they are. In other words, when I smile, that's what caused the pixels to change. So there's quite an easy sort of temporal relationship at least there. But temporal kind of asymmetries aren't enough. For instance, my barometer might always fall and then it starts raining. But then the rain comes after the barometer fall. So there's obviously something else going on there. So just a temporal asymmetry is not enough. A lot of people think, oh, cause always has to come before effect, but it depends if you're modeling the latent effect or the actual, the latent cause or the actual cause. So if it's this way around, which is how we're modeling VAEs, what it would say is that P of x given z, which is our conditional distribution, is independent of P of z. Now, what we're actually looking for here is Q of z. We've used Q because we're approximating it. This actually looks like the prior, but in reality, we're using Q for this. So just pretend that there's a Q there, because it's kind of the same thing. This is what we're actually learning, the distribution over our latent factors that we've learned. And we're saying that our marginal distribution of latent factors is independent of our conditional distribution. And so initially you might think, oh, that's weird. Like, surely there's some relationship between my distribution of latent factors and my conditional distribution. But there actually shouldn't be. Your latent factors should be completely independent in the way they're shaped, in the way they exist outside of your particular reconstruction of that. So if you're struggling with this, then relate it back to the altitude thing. It might seem, well, surely my distribution of weather stations contains information about the temperature at those weather stations. It doesn't. I can change the distribution. It has no effect on my conditional distribution. So they're a little bit like weird things to sort of get your head around, maybe the first time you experience this. Independence of mechanisms assumption, I think it's best explained with examples, so that's why I've talked about the barometer and the altitude one. And it also tells us this, which is our posterior distribution, P of z given x, is not independent of P of x. And that's actually what we want. We want the information of P of x to be in z. like the posterior, z given x. So that was that whole discussion that we just had a minute ago about, well, surely my latent space has to contain information about the image. It doesn't if you have a really powerful decoder, but it should based on this world model. Because when we're doing the inference process, i.e. going back the other direction, which doesn't change the world model, that's why we call it inference, we're using x to infer z. So if it were the other way around, and x caused z, which is not how we're modeling VAEs, and again, this is the PGM corresponding with the VAE here, that would mean that our posterior would be independent of our images, which is the thing we don't want to have, because that would mean our representation has no information about our images. So the reason why I'm talking about this is twofold. One, because these are a really good way of representing what's going on and what your view of the world is. And I think in deep learning there's a real temptation just to stick some keras layers together and sort of cross your fingers and just exploit some correlation. But we're not really generating any new information there. We're not generating understanding of the world. And I think if we're all in this department and we want to generate understanding and work on AI, we should be working on models that reflect reality and have some sort of basis in reality. It's a challenging task incorporating causality into deep learning. People are working on it. They're trying to learn these kind of graphs exploiting the asymmetries associated with the independence of mechanisms. So if you can measure the dependence between two distributions and you think, oh, surely these should be dependent, but they're not, maybe there's that causal thing going on. Maybe you're looking at a conditional that's independent of the marginal, and then you can start to infer things like causality, which generates knowledge about the world. So that's one reason why I'm talking about it. Second reason is because you can view VAEs from a PGM kind of sense, which has directional arrows in it, and therefore it's kind of useful to just see that this all ties up again with the independence. And if it was the wrong way around, we'd get that independence thing going on, which we don't want. Now, I don't know if any of you are doing semi-supervised learning. Anyone tried that? Any hands? No? One? We got one? Oh, two? Three? Oh, that's good. All right, so semi-supervised learning, for anyone that doesn't know, you've got a data set of, say, images. Let's use the images as the example. And they've got corresponding labels, but not for all the images. So some of your images are missing labels. And the idea is with semi-supervised learning, well, I guess twofold, that actually if you put pressure on the network to predict the labels that you don't have, that incentivizes it to learn more important features. But secondly, we may not always have labels for our data. So if we can get nice performance without labels, that's even better. Now it turns out that we can only do semi-supervised learning if we're in an anti-causal scenario. So when you're doing MNIST predictions and you stick your MNIST in and you're trying to predict the class label, that's an anti-causal system. The reason is that the label comes before the image. If I want to draw an image, I first think of the class and then I draw it. So the drawing is being generated by a latent variable. That latent variable, sometimes it's observed, so it's not latent, is the class of the image. So when we've got our network that starts with the image and then goes towards predicting this latent factor, we're in an anti-causal scenario because the label actually came first. And when you think about it, there's way more information in the observations, the images, than there is in the class label. Right? We've got stroke width, we've got handwriting style, all the rest of it. It's all the other way around. There's a whole load of latent factors responsible for generating that MNIST, and the way we do MNIST predictions is anti-causal in that regard. So if you want to do semi-supervised learning, this should sort of start ring alarm bells with this independence of mechanisms, because if you're actually in a causal scenario, these things become independent, and knowing more about my marginal, in this case it would be images of MNIST, wouldn't tell me anything more about the labels. And this is where actually it's beneficial that we're in an anti-causal scenario. So with MNIST, we're in an anti-causal scenario. We don't have this assumption being held true, which means that when we get some more images, it tells us more about the class labels, or the conditional class labels, conditional distribution. And the way that works is that if I've got, say, some images of ones, and I get some more images that look a bit like ones, but I don't have explicit labels for them, that's more information about ones. And it only works that way around. Having some more class labels doesn't help us, right? Imagine if it was the other way around and you had like 10 images, but like 10,000 labels. What are you going to do with it? And I think intuitively, we're like, well, obviously you can't do anything with that. But is it obvious why it does help the other way around? And the reason why it does help the other way around is because of this independence of mechanisms thing that's built into our sort of the structure in the world and how things sort of develop from latent factors to observations. Is that kind of okay? Bit of a brain dump. I think if you haven't experienced this before, it's a bit weird. But yeah, it's a really interesting field. I recommend looking at sort of Judea Pearl, but also the more academic work by Scholkopf, which is quite recent. So many problems may be amenable to incorporation of domain knowledge. And as deep learning people, as like computer scientists and machine learning people, we should be trying to sort of do our best for generating understanding, not just getting a hit count on accuracy scores. So with time, again, be careful. Time doesn't necessarily imply the right sort of causal mechanism, because you might be observing sort of a latent factor or some other factor that's not actually the cause. And interventional robustness, which I briefly mentioned before with regards to disentanglement, comes in as well. When, say, like medical fields, for example, are doing this, they will make a change to the model, like this person does get the medicine or this person doesn't get the medicine, and they'll see a corresponding output. And if their model's properly capturing the way the world works, they'll see a change in the prediction that does actually correspond to a change in whether or not they have medicine. It's not the same as just changing. Say you have a correlational data set, you can't just change the value. It's not the same thing. The do calculus sort of compensates for the complexity associated with causal modeling. Then you can actually make an intervention, which is different. Okay, so this is one way to test disentanglement, sort of taking a causal perspective.
So what happens when we try to disentangle things that can't be? I mean, if we wanted to, say, if there is the disease that only affects males,
right?
Okay, and now we are designing this algorithm to decide who gets the pills, right? And we want to disentangle it from gender, right? What's going to happen then? I mean, if we force that, is it going to be just like, let's give some of these pills to ladies as well, even if they don't care, are not affected by the disease, just to be fair? I mean, what happens then? I mean, what happens when we enforce something that...
So I guess this is like the whole, all models are bad, some are useful. I think if you have domain knowledge and you have to know have some domain knowledge, otherwise your model will be misspecified, you will get the wrong results. So you can certainly force these things to occur, and then like your model's bad, and that's kind of the bottom line, I guess. And that's the difficulty that people dealing with these decision-making processes have, that burden on themselves, because if their model's wrong, the model's wrong, like bottom line. I think that also points to the gold standard of like fully randomized controlled trials. Yeah. So they're great, but you don't always have that. So this is a little bit of a way of getting around that, circumventing. If you don't have randomized controlled trials, how would you pretend that you did? But if your model's wrong, yeah, and that's the importance about really thinking about what's going on in the world and whether your model actually reflects that. Theory is what they would call it in other fields. So like psychology is being really aware of what theoretical sort of notions underpin the data generating process. And if you don't know them, we don't often have to think about it. Often it's like, for deep learning people, it's like, what's the theory? Don't care. Chuck some data at it and that'll do. But okay, we should try and move beyond that, I guess. All right, so nearly done. So evaluation now, I hope you can see that evaluating VAEs, as well as all these generative or unsupervised methods, needs to be undertaken from lots of different perspectives. So I'm going to give you some ideas. We had these original goals: faithful reconstruction, but also high sample quality. This was for GANs, this was for VAEs. You can't reconstruct with a GAN. Have rich representations, lots of information in there. We want to do some good density estimation, learn whether or not our density matches the true density. Learn these generative factors, remove nuisance factors, and achieve some disentanglement. Might want to achieve compression. There are quite well established, I guess, methods of evaluating compression. Interpolation, we might want to move around in the latent space. And generalization, does our model generalize to sort of unseen data? So we can take the log likelihood, either in bits per dimension or in nats. So this is a bit like what we're doing with the proxy, the elbow. We compute an evidence lower bound on the log likelihood, and then we have an estimation for how well our density matches our true density. Reconstructions similar to this, but you can also evaluate them obviously qualitatively. So view your reconstructions. Do they look real? I've actually been in scenarios before when I've been doing some VAE stuff, and I've put together an old model, start feeding it data, and I've achieved a really nice log likelihood. Well, a nice-ish log likelihood. And I was thinking my model was working all right, then someone else was wrong, and I went back to the reconstructions and it was just garbage. And the color channels were all wrong or something. There was something with the original images. So that's another example. Like, you might be getting nice looking results, but are they meaningful? so reconstructions. Samples as well, and these are different, as I sort of stressed earlier. A sample is not the same as a reconstruction. You can generate great samples but have bad reconstructions. Many models have that, by the way, so I've seen many VAEs that have chased nice samples, and they haven't even said that they're explicitly doing that, and then they compare the input image with the reconstruction, and they're just like, these are completely different images. And they're like, look how good they are. Yeah, they look real, but they're completely different. So again, be mindful of the distinction there. Disentanglement, there's all those metrics, but also we might be able to do that qualitatively as well as objectively. Interpolations, can I move around in that latent space without coming across zero likelihood areas? Will I fall into a pit and I just get some bonkers result out? GANs are amazing for that. Like, you just have to sample slightly what it hasn't seen before, and you achieve someone with like their mouth on the back of their head and their eyeballs in their mouth at the same. Like, some of the stuff is completely nightmarish, and obviously you don't get that with VAEs at all. I've never seen like a face that is like Picasso style, whereas GANs love it. They're all over that. Rate distortion characteristics, so you can take that compression approach, and if you're using VAEs for compression, then that's worthwhile. And then latent space geometry as well, which I haven't talked about, which I'll talk about now. So let's say we have images that are just of dots of different XY positions, just very simple. In fact, if you look at the VAE literature that's just on VAEs, a lot of it looks like that. It's really exciting. And so the distribution of possible positions for that is there. It's just a uniform distribution over a square space. This is actually the geometry of that space. So what we'd like to do is, if we were to use a model, does it reconstruct the same geometry? The idea is that when I sort of perturb these images at the input, do I see a corresponding change that's sort of measurable on a grid? So you have like a two-dimensional latent space. Can you plot those changes? And does it correspond with what your input images look like? So ignore the one on the left for now. This is what a typical VAE model does. So this is beta VAE, probably the most well-known VAE. Beta VAE, that beta corresponds with that pressure on the KL. So they were the first people to sort of play around with that value. All right. Factor VAE is just complete gibberish. And it's like, well, this is kind of strange. We might get nice reconstructions, but our latent space is actually not learning something meaningful as such. So again, this is another way to check whether or not your model is actually intelligent. Is it actually sort of doing what you a priori expect? If you use spatial broadcast decoder, this is a bit like coord-conv. You incorporate some information about the position. So most convolutions position invariant, so it doesn't matter where it is, it sort of produces the same activation. But if you build the position into those layers, check out coord-conv if you want to see how that's done. It's quite straightforward. Then you get this. So this is actually inside of VAE, and so there are ways to really well encode position information. That doesn't necessarily mean you want to, right? So it might be that you want that position invariance associated with convolution, in which case this would hurt your ability to become position invariant. But I think for generative models, when you want to be able to reconstruct, say, an image in the same position as it was at the input, this makes total sense. You definitely need position. Otherwise, when I reconstruct this dot here, it'll appear up here or whatever. So. And the final thing I want to talk about is datasets. So when you go away from this talk and you're super inspired about VAEs and you want to apply them to everything that you've ever done or thought about, you're probably going to have to benchmark it using one of these datasets. So I'm going to sort of skip through these. These are just, they're all synthetic. These are all synthetic. And they're data sets that are quite useful for ground truth factors, evaluating your network's ability to say all the things actually, you know, is the information about, say, the car's rotation and appearance encoded in that latent space? Well, you need the ground truth factors for that, so you use one of these. Similarly for D-sprites, it's just shapes, some of them are different colors, different positions, different rotations, and so on. So when you start using VAEs, it's well worth sort of just evaluating them on these if you're working specifically on VAEs. Disentanglement dataset recently came out, which is actually real-life videos of robotic arm with objects of different colors, different rotations, and from different viewpoints as well. But they also have a synthetic version as well. So then you can actually test your network's ability to generalize between synthetic and real data, which is really helpful. I haven't used this data set, but I have a feeling it's going to become the new sort of benchmark data set for VAEs and VAE development. Ooh, what a marathon, here we go. What's next? Home time maybe, I don't know. VQ-VAE2, so I mentioned this briefly before. This is the target image, this is the reconstruction. I cannot see a difference. Like, even this little wisp of hair is there. Right? So VQ-VAE2 is way better than almost any GAN that I've seen. These are at the different resolutions of the space. And this network also produces latent spaces that have all the information in. They have to. Like, how else are you going to reconstruct where the hair is if you don't know where the hair is? So this was like real sort of like, wow, this is insane. The paper's a good read, and they've got samples online as well, I believe. So definitely check that model out. Essentially, it learns a latent space that's continuous because we have trouble backpropagating through discrete variables, but it has another layer of a latent space on top of that that quantizes it. And then we use that latent space that's quantized for the subsequent decoding. So it's a really nice idea. In order to get the really nice fine-grained reconstruction, I think they used pixel CNN. They used some autoregressive model on the output, but there was already pressure, and obviously the results speak for themselves. There's pressure on the latent space to learn useful embeddings, and part of that is, you go through these different sort of resolution levels. You have to produce all of them with good accuracy. So that's the one that I really wanted to mention as state of the art. I took this slide from a Berkeley lecture because I thought it covered pretty much everything. So what's next for VAEs? Exploring more modern decoders. Like, people are always coming up with better ways to generate images, and I don't mean in terms of like whether or not they use a GAN. I mean like in terms of their decoder architectures, having really powerful decoders there. It could be weakly autoregressive, it could be fully autoregressive. There are issues with autoregression when it comes to generating pixels because correlations in images don't follow a row by row order. So there's lots of different ways to sort of, I guess, leverage the autocorrelation in the image, not necessarily in a row by row fashion, but in a sort of a more kind of like, I don't know how to say it, a more kind of like, I don't know, make up a word. So more powerful posteriors as well. When we're using a variational posterior, do we have a sufficient one to regularize it against? Well, that'll be the prior as well. So prior and posterior. That's actually not on here, is it? Yeah, so using a more powerful prior is important, also more powerful approximating posterior distribution, and also hierarchical latent variable models. We've stuck with one layer of latent variables. It doesn't really make sense for many scenarios in the world. We should have a hierarchy in there that corresponds with our world model. So it may be that we have one latent variable here that causes another, but this hierarchy is separate to another latent variable which is sort of independent of those two, and so on. So we should try and again start to build our understanding of the world into our models, or allow our models to extrapolate that structure in the data. Finally, discrete latent variable models. There's still a lot of work being done sort of making our latent space work for both continuous and latent variables. As we've seen, the VQ-VAE2 just quantizes everything, but there may be ways, sort of intelligent ways to sort of use both. And finally, well, I guess you need to figure out ways to incorporate powerful decoders if you want to pursue generation accuracy without compromising the latent space. Because the only architecture we talked about was like the vanilla VAE, and so there's an awful lot you can do with it, and good luck, I guess. It depends on your goals. I think that's it. That's everything. That's everything. Cheers for coming. That's amazing. Can't believe you turned up. Got time for any questions, I guess, or you're going to go on GitHub and start plowing through it. Has anyone got any like applications that they would be ready to use VAEs on? Rich, tell me about yours.
No, I want to ask questions. So,
okay.
Because as you know, I'm a bit of a fan of mutual information.
Yeah.
In fact, everyone in the group knows. And Simon will know the transfer entropy. So given the mutual, I mean, the underlying mathematical model you've got is like, sits in entropy. Mutual information sits nicely with entropy. It's built out of it.
Yeah.
But then when you go into the causality, so what was the? I can't remember what you were talking about. Everyone's using. This calculus. So
do calculus. Yeah. Well, do calculus is more a way of.
But that's not based in entropy.
Well, it's still probability distribution, so you could easily relate it to entropy. If you have a distribution of data that's got an associated entropy with it, and then you could rewrite it essentially in terms of entropy if you want. But
nobody's applied like the transfer entropy, which I've talked about before.
No, people have applied it to sequential tasks.
But not to VAEs.
Not with VAEs. In fact, like the whole causal thing with VAEs are very limited applications so far. So people in deep learning are like very, very new to this. And so you look at some of the models that medical fields are using, and they're quite complex. They're more limited in their ability to map between distributions. So if you have an arrow between two variables, that basically means there's some function that maps this variable to this variable. We would be used to doing that. We'd just apply a neural network in the middle, which is what we do when we say an image predicts a label. Typically in the medical fields, they have sometimes less data, a lot of the time less data, but sometimes they have plenty of data, but they're not using neural networks and deep learning in the same way we're progressing that field. So when I look at deep learning, we're not really there yet. I mean, some people are using VAEs to predict generative structure. So they'll give it a whole lot of graphs, like they do graph-based, convolution-based essentially, and then they'll use the data to predict what's the most likely graph. And then it's sort of semi-supervised way of doing that, but yeah, it's quite young. I mean, I'm just giving a VAE interpretation from causality. People at DeepMind have done the interventional robustness from causal perspective, so they're doing disentanglement from causality, but they're not sort of making a weird VAE, they're just saying, how does disentanglement relate to causality? So, there's so much work to do. Yeah.
Excellent talk. Thank you for this. But I have a question, this VQ, could that be viewed as introduction of some noise on the latent space?
Vector quantization.
Because actually what we do, we actually vary the values before the reconstruction, and we do it depending on the likelihood. Because obviously when there is a lot of data, the clusters will be smaller. There's less data. The clusters will be
Yeah, very true. So you, I guess you would amplify clusters, like you said. So you make them more compact. You get quantization noise. Whether or not that's
I'm just thinking whether this is one of the reasons there is a this quantization noise.
Yeah, I guess it's like you add quantization noise, which is, I guess, intuitively something bad, but as a result, you simplify your ability to decode.
You're doing variational encoders. You add some noise in the
Yeah.
And in practice, what kind of, how many dimensions up we can go in these representations? This is like
for VQVA or in general?
No, in general.
In general, like you can actually have as many as you want. Like that's the beauty about that regularization term. It takes care of it for you. You could have thousands of dimensions and only need 2. If you only need 2, it will only assign 2 because of the pressure to remove information. If that pressure is weak, it will start to entangle it, possibly. It's really, really arbitrary. So a lot of the work that was done by Locatello recently on unsupervised models showed that actually these models just do whatever they want a lot of the time. Whether or not they assign a particular variable to a distinct ground truth factor is just like, I don't know, it's just random. So
can we go as high as 1,000 dimensions?
Yeah, it wouldn't affect any. I mean, obviously if you go down, then you start to constrain it, but if you keep going up, you'll find it plateaus and then you don't get any sort of benefit. So yeah, if you're concerned about how many you should have, always go for more, because it's not going to hurt the network because of that prior regularization. Yeah.
In the earlier slides, you showed that we usually have a vector part which encodes the mean and the other part which encodes the variance, right? So does the variance contains information? Can I interpret it that it is telling me how much I can rely on a particular dimension? So for instance, if I'm doing face recognition and I have got some dimensions where the variance is very large, I should not use those dimensions.
That's a really good point. So, and in fact, I don't think I put this on the evaluation thing. You can actually also report the KL. So how divergent are you across dimensions? And so the dimensions that have a variance very close to 1 are the ones that are much like your prior and they contain no information. So if your variance is a long way from 1, it could be less than 1 or greater than 1. You're going to have, well actually no, it's more likely to be greater than 1. It's going to have more information in it, and that's a way to pick out the sort of important dimensions that it's learned.
That's one thing. The other thing is when, for example, in testing, when I give it an input image, and it gives me a mean value and a variance value, right?
Yeah, okay.
How can I interpret the variance in that particular testing? Some confidence on the mean?
Well, usually when we put new images in, we actually, I don't know how to interpret that variance in that case, because it's not a distribution. You've only got one image. So the mean, I guess, means something because it tells you what value of a certain dimension you have, but the variance is just relates to the distribution that you're sampling it from. So I don't necessarily know off the top of my head how that would relate to what the image is like. I guess it would tell you something about, I don't know. I'd have to think about that one.
Does it actually give you variance when you test?
Yeah, so when you put an image in, you obviously have some value for the mean and the variance. The mean obviously the vector of means obviously corresponds with what values you have of any of those particular dimensions, but the variance, I don't know what that would correspond to.
One more thing, apart from the condition that the prior should satisfy, we should be able to apply a reparameterization trick on the prior.
Yeah.
Is there anything else the prior should have? What kind of prior should be preferable? More complex ones or simpler?
Well, I think actually there's like 2 points in there. So firstly, you don't necessarily have to sample from your prior. So your prior is just there, it exists as a way to regularize against it. So I compare what I've learned against that prior. It could be anything. In terms of what noise I inject to reparameterize, I could actually choose anything I want. So you can make it a Bernoulli distribution, but you'd struggle to backpropagate through a discrete variable then. But you could apply some kind of crazy transforms if you want. Yeah, it's kind of independent, up to you.
How does it relate to the accuracy of, I mean, would it be good to have like complex priors, or it doesn't matter much?
I think as with all Bayesian approaches, like your choice of prior is quite important. If you for instance, if you choose a uniform, it doesn't really have any effect, right? It can do whatever it wants. But if you have a Gaussian, that's quite a strong kind of implicit bias, that inductive bias, no, implicit bias that you're associating with the model. So you'd have to probably have good reasons for picking a particular prior. I have seen people using spherical priors before. So people have said, I'm going to encode something like rotation, it's going to be geometrically relevant. I know that rotation is going to come around every 360 degrees, got that phase wrapping thing. Therefore, my latent should be able to accommodate that wrapping effect. So I keep forgetting the name of it now. It's like a Gaussian on a sphere. It's like escaping me the name of the distribution. But yeah, that would be an example of it. If you have a strong justification for using it, then that's fine.
Does that really make that much of a difference though? Because there's two ways you can look at that. Are you actually forcing the latent space to have that distribution, or is it just like a Parson window and filling in the gaps in that distribution?
Well, I guess...
Because certainly when you're varying that beta, I mean, all you're really doing is bleeding to try and make sure your distribution is a continuous manifold, rather than actually it's Gaussian.
Well, I guess
you calculate divergence of that. So if it diverges somewhere, I mean, what happens, say, with the rotation, that if you rotate at 720 degrees, the cost function would go to very, very high. Yeah. So when you're doing traversals afterwards, if you want to keep pushing that value, you'll see it keep coming back round to the same thing. So it would certainly help for traversals. I don't know about learning as such, but the information should be in there. I guess then for downstream tasks, can your downstream tasks understand this sort of rotation inside the latent space? But yeah, it should make a difference. I've seen better results for people that haven't used Gaussians, for instance. I can certainly go that far because they are so restrictive. You know, nothing in the world is actually Gaussian, and apart from a infinite sum of like all these independent variables.
If you sample anything badly enough, it's always Gaussian.
And enough times, yeah.
My questions might relate to the previous one. So if I want to use a bottleneck of the VAE as a representation, so like which layer specifically should I use? So we have a mean, the log of the variance, and we have a z.
Yeah.
Should I mean plus or noise with that?
That's a really important point. So usually people just use the mean. So they chuck the variance away, and they just use the mean vector. And the idea is that all your regularization has been done because of the noise. So what it's learnt in there should represent what you want it to represent. So it's a bit like taking a maximum likelihood approach. You're picking the peak of the Gaussian essentially, and then they use that. So you run your data through it, you extract the means for every single one, and then you use that in a downstream task. That's the most common approach.
But usually the reconstructed image is getting from both the mean and the variance.
Yeah. And also interestingly, most people that just sample only use the mean as well. So when you sample from an image, you just use the mean. And I think it's because you want to bypass the z. So you have mean, variance, and then z, which is your sample. But this sample has lots of noise in it. In other words, every time I pass the same image through, this sample will be slightly different. Yeah, exactly. Yeah, so there's that stochasticity in it. And if you ignore that and you just feed the mean in, you tend to get slightly cleaner results. So it's more useful during training than sort of test or test or deployment, I guess. Any other questions? All right, I think we're done. Are we? Yeah. Oh, thank you.
just wanted to say a big thanks, because 3 hours, it's non-trivial to talk non-stop for 3 hours, but it's also the amount of work that you put into reading all the papers and putting it all together. And I'm particularly glad that we managed to record it.
Cool.
So
Yeah.
that if you get run over by a bus, then we've got a record of
No
this.
worries. No worries. Insurance policy.
So thanks, Oscar.
I really appreciate that.